Good afternoon, PCS members and friends. Today we have a seminar which is a part of our advanced study group business, and today's scientific host is Bruno Tomasello, who will present our today's speaker.
Bruno, thank you for the introduction. So this is actually the last one of the seminars of the advanced study group. We have the pleasure to have with us Professor Tomi Ohtsuki from the University of Sofia, Japan. Professor Ohtsuki completed his PhD at the University of Tokyo in 1989, and he has worked on several topics spanning from Anderson transition, conductance fluctuations, Hall and spin-Hall physics at the nanoscale. And over the last decade, he has dedicated much of his activity in three-dimensional topological materials, such as topological insulators and balsamic metals, and he has developed interesting randomness on topological materials, and also has done extensive studies, including neural networks and deep learning for physics. And today he will talk to us about using and analyzing quantum computation for material phases classification and entropy dynamics. So let's welcome the speaker.
Thank you very much. I would first like to thank Bruno and the team for inviting me to IBS again. And today, what I'm going to talk about is the usage of quantum computation to classify the material phase, as well as analyzing the quantum computation and study the entropy dynamics in during the quantum computation. It is based on the two papers I recently published. Let me introduce the topics. Quantum computers promise to revolutionize computation, tackling problems intractable for classical machines. And one key area is understanding complex quantum systems, such as quantum material and quantum dynamics. And this talk explores two facets. This talk consists of two parts. One is to use quantum computer to classify the many-body wave function. And the second topic, which is the main topic of this talk, is understanding the monitored quantum system, developing the theoretical tools to describe the universal behavior of the entropy dynamics. I'll explain what I mean universal, but let me start. So the first part is about to improve the quantum convolutional neural network. And for that, I use concept of, I added a concept of quantum channel attention to quantum convolutional neural network. This is not related to attention mechanism of large language model, but old type attention mechanism. So let me explain quantum convolutional neural network. This is the analog of quantum classical convolutional neural network, and it is promising for quantum machine learning task. Are anyone familiar with quantum convolutional neural networks? Okay, but you will see it's just simple. It's just simple. They typically consist of convolutional and pooling layer, just as in the case of classical neural network. And the key advantage is that QCNN do not suffer from the plateau problem. That is exponentially vanishing gradient. So the training is quite smooth. Another problem and related to this advantage is that the number of parameters in QCNN is much less than the classical convolutional neural network. And we'll develop this idea and apply it to detect the quantum phase transition. using the quantum state as a direct, many-body quantum state as a direct inputs. But before that, let me show you the classical convolutional neural network to compare with the quantum one. I think I gave a talk about this some years ago, about the classical application of the classical convolutional neural network to distinguish the phase. In the classical convolutional neural network, we input the photo of a cat, and the output is the probability that this photo is a cat, or the probability that this photo is a photo of a dog. Now we apply it to physics. This is the input is a three-dimensional wave function, or a wave function, square of the wave function amplitude. We transform this image to a different one by using the process called convolution. That is, these dots are the wave function amplitude square, and we multiply weight parameters to each of the point wave function amplitude in this cell, sum over them, and we get a new number. By shifting this cell one by one, but fixing this weight parameter, we get different figure, different image. And if we change this weight parameter, you get different image. So you have a series of different images, and that's the convolutional neural layer. Then we go to the pooling layer. Pooling layer means that we pick up, for example, 2 by 2 by 2 cell and take only the largest value inside this cell to reduce the degree of freedom of this process. And that's of the image. And by iterating this process, and this neural network becomes deep in this direction, we do the deep learning and classify whether this wave function is metal or insulator.
Sorry, I have a question. Usually we need to perform some scaling analysis to judge a metal or insulator. Do you mean that you need to train your network on systems with various sizes, right?
Well, it's the advantage that we don't need to go to a very large system. We know, let me go to the next slide. So we know by the transfer matrix calculation done by Keith that this is a critical point, independent calculation. So we prepare the wave function 40 by 40 by 40 cubic and gather the data along this small region, which is localized, and then we diagonalize the system along this small region and prepare thousands of wave functions corresponding to this parameter. And then let the neural network decide whether it is localized or extended. It's not only this one, but if you change the parameter from box distribution random potential to Gaussian distribution, without further training, we can draw the phase diagram like this. And if we change it to Cauchy distribution, the random potential, let the random potential to obey the Cauchy distribution, we get a different phase diagram. If we apply magnetic field, we get this phase diagram, which shows the breaking of the time reversal symmetry, and some insulating phase here becomes metallic, which is predicted by the neural network. And we can also analyze the quantum population problem once we train the neural network in this small region. So, and this is the This is about the classical neural network.
So when you say there's one region, where is the region?
Oh, what? White region?
You say in a small region, it's trained.
Yes, this green region is trained.
It's literally
Training region. Other region is not used for training. What you see is a boundary, even the boundary localization can be well detected by this neural network. And even this, if you set energy for something like slightly above 6.0 and move it, you first have an extended state and then localized, you first have a localized state, blue region. Then you enter into the delocalized region and then localized region again, which is a known phenomenon for reentrant phenomena or the boundary edge localization, which is nicely detected by the neural network.
So, but sorry, for the neural network, for every point, you just diagonalize one wave function.
Yeah, diagonalize
One wave function for every
one
point.
Hamiltonian
Yeah.
and pick up the and diagonalize one Hamiltonian, and then you will get the whole wave function along this energy spectrum.
Oh, I see.
Yeah.
Okay.
And then I input each wave function and let the neural network decide.
But how big is you for that
You mean
for that parameter? What how you take the same size you took for the training?
yes, same size to the training. TN is better using the neural network that can be applied to a different size. But in this study,
Yeah, you're not doing
Yeah,
finite
yeah.
scaling, but that's the big
yeah,
difference.
I only use 40 by 40 by 40 system.
Okay, so you avoid doing finite size scaling.
No.
And you don't do sampling. I mean, you
No.
just do one
Yeah, just
sample
one.
of each.
yeah, but these points, 5 dots are averaged, actually. So there is some average. Because, along this line is the 40 by 40 by 40 system. So I have 64,000 wave points along this direction. And the Python snares out. Anyway, this is the convolutional neural network in the classical sense. Now, this is the schematic figure I just showed you. And in the quantum convolutional network, instead of psi squared, we input the psi itself.
Yeah.
Then we apply the unitary gate U1, U2, and U3, which correspond to the convolutional layer. The value of U1 is fixed, just like weight parameters are fixed in the classical neural network. Then in the pooling layer, remember that we consider a small cell and take only the largest value and throw away all the other data point or wave function. Now, in the case of quantum convolutional neural network, it's a bit tongue twister. We measure the qubit and throw away the result of the qubit and reduce the number of the qubit. Then we do it again and measure it again. And after this, we measure the target qubit. These are the target qubit. And depending on this value, 0 or 1, we decide which phase this wave function belongs. That's the idea of quantum convolutional neural network. So the correspondence is that the unitary gate corresponds to convolutional layer. The measurement gate corresponds to pooling layer.
But you're still, sorry to be
Yes, please.
very basic, but I mean, you're doing this on a classical computer using
Yeah,
complex arithmetic.
yeah,
You don't need it.
because, yes.
So the
Yeah,
quantum
it's
city
just
is
a
the phase.
simulator.
Okay.
Yeah,
But in
classical.
principle, you could do this all on a classical computer.
Yeah, I think one of my colleagues tried using the IBM. But it doesn't go beyond this because of the noise.
No, but yeah.
It's so noisy. We couldn't.
No, I'm asking the opposite question. I mean, you can do this computation, but you have to do complex arithmetic and not just look at real numbers. But you could do all that complex computation on a standard computer. I mean, you don't need a quantum computer.
Yeah,
Is that correct? Or?
Yeah, that's correct.
But the point is why it's called quantum computing is because presumably you can do much better on a real quantum computer.
Yes, I'll explain it to you.
Okay. Good.
Because I already, I may be able to explain. You see, there are many parameters involved in the convolutional layer, and sometimes or often it's more than million, or in the large language model, it's trillion. Now, let's count the number of parameters here. U1, this is just 2 qubit, this operates on 2 qubit. So it's a 4x4 unitary matrix, which have only 16 real numbers. So we have 16 real numbers. We need 16 real numbers to calculate this U1 gate, another 16 for U2, another 16 for U3. So we end up with 16 times 6 parameters, which is less than 100. So less than 100 parameters are needed to construct, to fine-tune the neural net, quantum convolutional neural network.
How you do
This is 1/10,000 reduction of the number of parameters. Please go ahead.
How you do the training for this network?
You mean the training of?
Change the parameter.
I leave it to Qiskit. There is a library to train the neural quantum neural network.
So
I just rely on.
because for each time you feed the data in, you need to change the parameter U, right?
Yes, again, I do the supervised training.
Yeah.
That is, there is a model that we can solve analytically, and we use the solution of the many value wave function and input it, and we know the result that that wave function belongs to topological phase or just paramagnetic phase or antiferromagnetic phase. And by doing so, we train we tune the parameter of U1 and U2 or the unitary case. Let me go, because you will know the process. So that's original quantum convolutional neural network, which was proposed in 2019. And what we did is the following. We thought that this wasted qubit in the pooling layer can be used to improve the QCNN. That is, we utilize a measured wasted qubit, and instead of wasting them, we use this qubit and weigh, according to the measurement result, we weigh the result of the result of the observation. That is, in the final stage, we get the distribution of the measurement. We do a measurement again and again, and we get some histogram, something like this. We do the measurement again and again, and we get this measurement result. But this measurement result, our distribution, depends on the value of the observed qubit. So when we observe zero in the intermediate region measurement, we get this distribution, and when it is one, we get a different distribution. So we use this information and weight it to improve the classification. That is, we want, if this is the real label of the input wave function, we want it to be almost one. And in fact, what we did is this kind of result. What we obtained is that by using this wasted qubit, we get a better classification of the input wave function.
So in
yes.
in the classical
Yes.
CNN, then basically you need the parameter like go exponentially with the system side, right? And here it go linear.
Yeah, here is linear because we are even for system size 20 or in the classical one it's 2 to 20, but in in this quantum computation it's just 20. Thanks. So as an example, we consider the binary phase classification of plus Ising model. It's not a simple Ising model. If we consider only this term, it's just an Ising model. If you add this term, it's an Ising model plus longitudinal magnetic field. But we have another term which we call the cluster term. Here, yes, in the world of quantum computation, we don't use sigma x or sigma y or sigma z, but we use large X and large Z. So let me use this notation. And in this system, for small gx and gxx, but large g, zxz, zxz, we have, there are here symmetry protected topological phase, which can be written explicitly like tensor product of L qubit, where plus is eigenstate of sigma x or x. Here, Cz is the control Z acting on qubit n, which is the control qubit, and n plus 1 is the position of the target qubit. And this is this cluster state is an eigenfunction of this operator where n varies from 1 to system size n. We know that for Gx is 0, the energy gap delta is just 2 times G, this parameter minus Gxx. So without these parameters, it's just 2 times the Gzxg. It vanishes when Gzxz is equal to Zxx and undergoes a phase transition. So this is the solution we know. Let's set Gx equals 0 and vary Gxx. When Gxx is equal to Gzxz, which is this point, it undergoes symmetry protected topological phase to paramagnetic phase. If Gxx becomes smaller and smaller and becomes negative, and negative enough, then we get into anti-ferromagnetic phase. That is what we know. Now, this is the result of the neural network classification, the classification by neural network for various Gx and Gxx. And this is without attention. I mean, this is the original QCNN. And this result is with attention. That is, we use the qubit intermediate measurement result to intensify the classification. And this white line is the training region. So I prepare a lot of wave function along this line and train the neural net. Then we prepare a lot of wave function in this parameter region. And only we take ground state. So each parameter has a single. Each parameter corresponds to a single Hamiltonian, and the ground state is obtained by diagonalization.
So sorry, you're doing
Yes.
exact diagonalization on chain
Exact diagonalization. Yes.
with open boundary condition or anything?
I think I used open boundary condition.
The color map
Mm.
or the one at the center is the same. So
Oh, okay, it's a probability that the state is topological.
yeah, value is
And the yellow means it's not well classified.
Yeah.
So, as you see, with attention qubit, the classification becomes much better. And let me go to next slide. Let me focus along this line. And we expect that it is not topological up to certain region, then becomes topological, and then becomes non-topological again along this line, which is the following. Here, the red dashed line is the exact solution. This black solid line is without attention, the original quantum convolutional neural network. And the other lines, blue line is with attention qubit only one. And if we increase the number of attention qubits, the phase transition becomes sharper and sharper. And this is the error function or loss function as a function of the number of training. And without attention, the error function or loss function doesn't decay quickly. Whereas if we introduce attention qubits, which is an intermediate measurement result, the training, the error function becomes smaller and smaller and more quickly. So this really works. So it's a short summary of this part. Quantum convolutional neural network works for classifying the quantum many-body state and using the result of intermediate measurement. Intermediate measurement is this measurement result of these qubits. Instead of throwing them away, higher accuracy and more efficient learning became possible. And I showed you only the result we use the attention qubit at position 1. But actually, the error function is almost independent of the position of the attention qubit. So, and as I told you, classical CNN involves millions of parameters, whereas QCNN involves fewer than 100 parameters. And I have to say that this is not completely quantum computation, because in the last stage, these are the result of the observation of the target qubit. Then I use the classical computer to intensify the results. So this is rather a hybrid quantum classical machine learning process. Yes, please.
So from the figure, it seems that you are working with 7 sites always? Or?
Yeah, because the figure becomes too complicated. But what I did is 18 sites.
I see.
Yeah.
And when at the very end, how many qubits measurements are you looking at?
Only 2 qubits.
Okay,
Because actually I wanted to classify three phases.
okay,
And to classify three phases, one qubit isn't enough because I get only 0 and 1. So I consider 2 qubit as a target qubit.
I see.
Did I answer the
Yeah,
question?
yeah.
Yes, please.
Sorry, probably I missed your explanation, but could you comment again, how did you use this attention qubit to improve the accuracy? Is there certain protocol that
You mean how to use the attention qubit?
Yes.
Yes, we measure if this attention qubit, and if you get 0, the target qubit measurement is this, and we accumulate the measurement result and draw the histogram according to which correspond to the attention qubit 0. And if you measure attention qubit 1, then you add the target qubit result to this histogram. So you have two kinds of histogram depending on the value of attention qubit.
So does this mean there's some correlation or entanglement between?
Yeah, there may be a correlation, but that I didn't take into account.
So actually here you take the idea of like collapse function after you measurement.
So can I ask one question?
Yes.
So since these are qubits, why can't you use two non-commuting measurements to specify 3 phases with just one qubit?
Non-commuting measurement, what do you mean by?
Meaning, let's say I run the same wave function 2 times.
Oh,
Once I run it and I do X measurement. Once I run it and then I do Z measurement.
oh yeah, that I didn't. Yeah, no, I didn't. So that I didn't try. Maybe it will improve.
So can you apply this and ask the symmetry breaking term to see how you out of the SPT phase?
You mean application to what?
I mean, you can ask the symmetry breaking term and then tune like how last the symmetry breaking can change you from SPT phase out of that.
That I don't. I never thought about. Okay, half an hour passed, so I will move on to the second part, which is related to this topic, but more physics is involved. It's not at all machine learning, but now that we see the importance of measurement in this quantum computation, we investigate the physical property of quantum computer. That is, instead of considering the quantum computation setup as quantum computer, we regard the quantum computing setup as a new type of material and investigate the property of quantum computing setup, such as entropy dynamics of this system. So the second part is that about the universal stochastic equation of monitored quantum dynamics. Monitored quantum dynamics sounds might sound new to you, but it's just a system with measurement. So monitored means measurement. The core idea is that the quantum system evolve under unitary dynamics, just as I showed you by applying the unitary gate, and then we did measurement. Unitary gate scrambles information, whereas measurement acquires information.
Sorry, one question. When you say measurement, you mean the in between the dynamics?
It's more subtle in this. Yeah. I will explain it to you. It's called weak measurement. What I'm going to talk. And here I will show you the analytical result of dynamical purification phase transition. So there is a competition between unitary evolution and measurement. Unitary gates makes increase the entropy. Measurement decrease the entropy. So there is a competition between them. And there is if we increase the frequency of the measurement, we get the dynamical phase transition in open quantum system. And it is studied, this topic is studied in various models, like quantum circuit, which is a set of qubits that I showed you, spin system or fermionic model. And fermionic model includes complex fermion and biolara fermion, as well as there are bosonic system application to this dynamic.
What do you mean by using the unitary increase entropy? I thought that unitary will not introduce, like, not increase entropy, right?
You mean the entanglement? Yeah, I haven't studied the entanglement entropy in this project, but I can calculate.
No, but my question is that if you consider the entropy, then unitary will not increase.
Unitary does not increase the entropy. Yeah, but how about the entanglement entropy?
And if you cut the system in half, then it's correct.
Yeah.
If you put the system in whole, then
Yeah.
no, unitary.
Yeah, unitary.
But then the evolution is not unitary. It's system.
Yeah, if it's an open system, then it doesn't.
Yes.
Let me proceed because I'm running out of time.
Doctor, question. So decreasing entropy, you mean that you will decrease entropy of your subsystem, but in general entropy will increase, of course, right?
You mean general?
I mean that you have some device and some system which you want to measure, but then if you combine them, you will also have some unitary dynamics, and then your entropy will increase probably, right?
Yeah.
System entropy.
System entropy.
Because you know more information about it.
Yeah. I just wanted to check it. I'm not able to entropy.
No. So what I'm going to show you is the entropy dynamics of this monitor system and the influence of the symmetry or universality classes on this dynamic. This is just a schematic graph that in the case of Anderson transition, conductivity vanishes if we increase the strength of random. That's the metal-insulator transition. Here, the measurement-induced transition says that entanglement entropy vanishes if the frequency of the measurement becomes exceed critical value, threshold value. So we see some similarity or analogy between them, but it's not this schematic analogy. But now we know that both Anderson localization program or the quantum wire and monitor disordered quantum wire and monitor system can be mapped to the same nonlinear sigma model, which I won't go into detail today. The only exception that we take replica limit 0 for quantum wire, whereas we take replica limit n equals 1 in the monitor system. And the second part is the focus of this talk, which I will explain in the next 10 minutes. It's a distribution, that the distribution of the quasi one-dimensional quantum wire the conductance is described by transmission eigenvalue, which takes a random value, and they are described by Fokker-Planck equation. And the same Fokker-Planck equation appears for the eigenvalue of the density matrix, which I'm going to show you. So let me go back to an old problem of conductance fluctuation in quantum wire, which I feel a bit nostalgic because I did this work when I was a postdoc, 35 years ago. So we consider a series of quantum dots and increase the number of quantum dots and study how the distribution of the transmission eigenvalue changes as we increase the length. Well, we can consider a wire and increase the length of the wire and investigate how the distribution function changes as we enlarge the system. This is an experimental setup of the two-terminal conductor. And and the Landauer formula for two-terminal conductance says that conductance is a trace of T dagger T. T is the transmission coefficient matrix. We can diagonalize T dagger and T and get the transmission eigenvalue Tn. We transform it to lambda n. And this lambda n obeys the Fokker-Planck equation written as this, where S corresponds to the length of the system. So if we change the length of the system, the distribution function changes. The distribution function with this transmission eigenvalue changes according to this Fokker-Planck equation. That's what we already know for the quantum transfer. Remember this type of Fokker-Planck equation with omega, this kind of hyperbolic sign form. Now, in this case, we have a universal conductance fluctuation like this. And because we know the distribution function, we can calculate the variance of conductance, which is exactly obtained by 2 over 15 beta. That is already known in the physics of quantum wire. And beta controls the symmetry. Beta equals 2 correspond to unitary, 1 correspond to orthogonal class, and 4 correspond to symplectic class. And this is what we know about conductance fluctuation. Now, let me go to this. Let me discuss the entropy dynamics of monitored free fermion. I want to emphasize that this is a free fermion system. So we have a lot of fermion, but they don't interact. Only we need to consider the Pauli exclusion principle in this setup. So we have a series of fermion on this site, not fully occupied. Then they evolve according to the Hamiltonian like this. But we can consider the two-dimensional Hamiltonian, or you can consider that this unitary evolution is completely random using the random unitary matrix. Now we do the measurement. The red point is the measurement. We do the unitary dynamics again and do the measurement again and again. And we investigate how the entropy changes as we increase the time. That's what I'm going to study.
So the 2 dimensions is 1 plus 1.
Yeah, 1 plus 1t. So we don't have an Anderson transition. If this Hamiltonian is 2D, it becomes 2 plus 1 equals 3. So we expect Anderson transition in this situation. But here, It's just one dimensional and constant. No randomness is involved. The randomness comes from the measure. Okay, we consider the fermion on the chain described by this Hamiltonian. But this part is not so important. We can change it to two-dimensional, or we can just replace e to the minus IH to random unitary matrix. The universal value is the same for these cases. And for observable, since it's a spinless fermion system, all we can observe is a number, or particle number at site I. So this is what we observe, what we measure. Then the class operator for a weak measurement becomes something like this, where Ni is Ci dagger Ci, and this dwi is a random variable which obeys here I assume to Gaussian distribution. Now, setting the initial density matrix as rho 0 as I divided by 1 over 2 to the power L. L is the number of sites. This is to make the trace of the density matrix to be 0. And this I is 2 to the L times 2 to the L unit matrix, which is huge, even for a small number of sites. In this assumption, every Fock spaces are equally mixed, so it was in finite temperature initial condition, where all the states are completely mixed with equal probability. But I will show you that this the result is independent of this initial value. We start this rho 0, multiply a unitary operator U, then measurement operator N, again and again until we get M. And the density matrix at time t is given by M dagger. But again, I want to emphasize that these 2 to power L times 2 to power L large matrix, which we can't simulate. And actually, there are some works which try to simulate this situation up to qubit number 6 or 7. But what I'm going to show you is that this error is 1,000. How do I do that? In the calculation of this density matrix at time t, we need this calculation. Both the measurement MT and the unitary evolution UT includes creation and annihilation operators. So they are, again, as I said, it's 2 to the L times 2 to the L matrices, when the number of sites is L. But we can use the fermion's Gaussianity, which and they are reduced to only L times L matrix combination. So what is Gaussianity? Generally, exponential to C dagger C. C is the vector of the creation annihilation operator times exponential C dagger YC is also can be expressed as exponential to C dagger AC. That's the Gaussian for free fermion. And another thing is that e to the A, this is a matrix of, now it's a matrix of L times L, not 2L, 2 to the L times 2 to the L, but L times L matrix. A is just a multiplication of e to the X and e to the Y. So that makes the calculation quite simple. So U is just unitary U, which is originally C だが e to the minus e to the C だが minus IHDTC becomes just e to the minus IHDT. And the measurement is just expressed in this way. So this please note that if the creation and annihilation operators are involved, I use this form. But if it's just a matrix, then I use the standard italic phase.
So the reason you can do this because both
Yes.
So the reason you can do this because both unitary and the measurement are Gaussian, right?
Yes, Gaussian.
At like
Yeah, well, both of them are Gaussian to do the large system. And we need a large system to observe universal property.
So you have the integrable system.
Yeah. But I think some of the aspects are so universal. I think even if we consider many-body interaction.
So we have a free framework. Can you map back to the use the Wigner transform map back to the spin system and simulate this on a quantum computer?
But in that case, the situation might be worse. You mean the Jordan-Wigner
Right.
transformation?
Right.
I don't know.
Because you can,
Will it simplify the calculation?
no, I mean because you can use it to do the experiment on IBM.
Oh yeah, the qubit. Yeah.
Right, because the measurement and the two qubit gate is available, right?
Oh yeah. Yeah, IBM Q. Yes, but I did is 1,000 systems. And I won't be allowed to use
IBM
1,000
now
qubit.
If you 440 qubit, 340.
Okay. So now that we can do this MT calculation, just like a transfer matrix calculation, one by one, multiply U, M, U, M again and again. And what we get is M naught from 0 to T. And then the final result, the density matrix, can be expressed as this, and this P matrix is expressed by e to the 2p equals mm tan. And so this P matrix can be expressed only by L times the matrix calculation. Okay, but we consider matrix called correlation matrix, which is defined as follows, which is the expectation value of Ci dagger Cj. So it's just a green function. And this has information of this system. So we define this Cij as this and consider this as a matrix element of correlation matrix C of I and J element. And to calculate this, this Cij is expressed by hyperbolic tangent P, where P is given by this equation. You might think that we need to take log of this and insert it to P. But since it's hypertangent, we can rewrite it to this form where C is just e to the minus 2p. So we use the transfer matrix calculation like this, and then we get e to the 2p, take the inverse of it, and add 1, and then take the inverse again, and we get C. And this C has all the information on this. Yes, 5 minutes. Okay, so this is how we derive the situation equation. But let me show you just one expression of the entropy. In this entropy, it's a Renyi entropy I'm going to consider, and which is defined as follows. And this involves creation and annihilation operator. We take the basis that it is diagonalized like this, and insert it, this result of the diagonalization, and we end up with the following expression that using the eigenvalue of rho t, or eigenvalue of the matrix P that I showed you before, using the eigenvalue of P, not which we call Z, we can express the entropy as this. I skip this part. And now we need to consider how the distribution of the eigenvalue Z changes as a function of time. And this can be done perturbatively using the second order perturbation theory, and I just skip it. And finally, we get the following Fokker-Planck equation. That's the distribution of the eigenvalue of the density matrix obeys this Fokker-Planck equation, where this is just time t, n is the number of Fermi, gamma is the strength of measurement, mu and nu gives the drift term, which comes from the measurement, and these are the diffusion. We actually for forced measurement, which I don't go into detail, the situation becomes even simpler, but I just skip it. The important thing is that we can derive the exact solution to the Fokker-Planck equation, which is expressed like this. You might think this is surprising, but we have some experience in dating back to universal conductance fluctuation. So we know approximately how the solution to that kind of Fokker-Planck equation takes. So this is the result of the Fokker-Planck equation, and we can do the mean field approximation. This is the numerical simulation result. Let's say these points are zeta, the eigenvalue of the density matrix. And as we change time, they do the random walk, but in certain velocity. And so these are the distribution of the eigenvalue of P at time 10,000 in this case.
Sorry, what do you mean by my mean field approximation here? What is it?
What is?
Mean field approximation.
Mean field approximation is that this is the, how can I say, this is the distribution function. And we know the solution, which can be written like this. And this, we can find the stationary point of W.
Mm-hmm.
That is, we can take the derivative with respect to Zn and set them equal to Z. And this is the mean field solution. And these lines are the mean field solution. And the fluctuation along these lines gives rise to entropy fluctuation. And I think it's almost getting time. There are several, one assumption is that we are considering a very large set of fermions and consider a uniform distribution of Z. And once we assume it, we can express the entropy of this. And in fact, the numerical calculation nicely coincides with what is predicted by this equation. This is particle number dynamics. This is the particle number at site 1, site 2, site 2, up to site 100. And this is the time, and the site number changes as the time goes by. But more interesting is the entropy fluctuation. And in fact, we can derive the explicit form of the variance of entropy. And for linear entropy, alpha equals 1, which is von Neumann entropy, we get this value. And for linear entropy, alpha equals 2, we can obtain exactly the entropy fluctuation as this, and so on. And
So
here is the
in the 2D map that you showed, the vertical
Yes, you
axis were the
mean,
time steps.
this one. This is the average of the number ni. Some sites have smaller ni. Some sites have larger ni.
So basically,
And this is as function of time. So here the electron density are less than the other part, the black part. And this changes quite randomly.
right, so basically it conveys the message that it changes.
Yeah. Okay, this is a numerical confirmation of the entropy fluctuation, which is almost constant, suggesting the universal entropy fluctuation. But please note that the time is changed from 0 to 2000. But still, the entropy fluctuation is almost the same. The value of the average entropy itself changes quite rapidly as a function of time t. But entropy fluctuation is, or the variance of the entropy is almost constant. And if we change the universality class of the Hamiltonian or the unitary evolution, this is the most general unitary matrix, random unitary matrix case. And this is in the presence of time reversal symmetry. And this is in the what is called class D, which corresponds to dirty superconductivity. And the variance changes according to the universality class. These are S2, S1, and linear entropy 3, 4, and infinity. They are all consistent with what we predict. So let me summarize my talk. The first part is about the usage of the quantum computation and introducing the measurement result as a channel attention. And the performance of the QCNN become much better. And then we consider the monitor dynamics, and we observe the universal stochastic, we derive the universal stochastic equation, and that can be solved exactly. And we obtain the universal entropy fluctuation. Universal in the sense that it is independent of the types of the measurement. I showed you, I mentioned forced measurement and Born measurement, but even if you do the projective measurement, we get the same entropy fluctuation. It is independent of the initial density matter. And also it is the same Fokker-Planck equation as in the mesoscopic metal wire system. So from that respect, I score universal entropy fluctuation. And thank you for your attention.
Any questions?
Yes.
This entropy fluctuation that you calculated, is that for a certain value of the measurement strength? Or
No, it's universal. It's independent of measurement. So a measurement type of measurement.
the Fokker-Planck equation is dependent on measurement strength, right?
Okay, the Fokker-Planck equation, you mentioned this, yeah.
So the gamma is
this gamma depends on, yeah.
And then when you write the mean field solution, that also depends on the measurement strength. I just saw.
Yeah, right, yeah.
But then why is the variance now independent of it?
Okay, I forgot to tell you this condition.
Okay.
Yeah, this condition should be satisfied to observe. Because in the long time limit, the entropy goes to zero. Just like in the long wire limit, the conductance is always zero. Exponentially becomes exponentially small for a very long wire. And so is the case in this. For a very long time, the entropy decays exponentially. But there is an intermediate region for finite n. And if n is large and gamma t is not large, then we observe the gradual decay of the entropy as this and the universal entropy fluctuation.
But then what I would ask is that in the context of this type of monitored dynamics, by increasing the measurement strength, it's possible to get to the quantum zero regime. And what would be the equivalent in this case? Because you are saying that entropy goes to zero nevertheless. I mean,
okay, there are assumptions that gamma delta t isn't large.
Yeah, that's right.
Yeah, but as you said, there will be a quantum zero effect, but we can't treat it in a formulation.
You cannot.
We cannot.
Meaning you will not get something exact, probably, but if you...
I don't know. I don't know. These are based on weak measurement, where gamma is quite small.
Other questions?
Can you perhaps go?
No, that's maybe one more question.
Yes, please.
The way you define this, or the way this whole thing is being done, it's just like a map. So you start with something, then you apply this map time and again.
Right.
And you are also calculating these eigenvalues of this, as you, and I mean, in a sense, because you introduce now, because you now introduce measurements, the dynamics is not really unitary.
No.
It's not linear.
Yeah, yes, as you correctly pointed out, this is unitary, but then
because you have this expectation value of k0 going in, so it's no longer linear anymore.
Right, yeah.
So my question is, I mean, I had this thought for a long time, but I don't know what it means. So if I now treat this map as just classical, because now it's it's non-linear, and if I calculate the Lyapunov spectrum of it, does it mean anything?
One difference is that this epsilon I is random. So at every time m is random. If this value is fixed, then it's just a nonlinear dynamics and non-Hermitian dynamics. And you converge to the eigenstate whose eigenvalues negative. No, imaginary part of the eigenvalue is the largest. But since this one is random, the non-Hermitian Hamiltonian is not fixed. So the eigenvalues or eigenvectors
there will be
points in
fluctuation, but I can still choose to calculate the Lyapunov spectrum, and
yes,
it will probably fluctuate around certain value. My question is, does it physically mean it?
Actually, I didn't show you. I'm afraid I didn't show you, but this calculation, you notice that it's a very long time.
Right.
And then this I did some Lyapunov exponent calculation.
Okay.
Yeah, I didn't diagonalize it, but just do the QR decomposition
Okay.
to get. So I showed you the intermediate region, something around here, but with the particle number more than 100 around this region, and showed you the universal entropy fluctuation.
Okay.
But here in this region, we can't calculate the matrix. No, we can't calculate all the eigenvalue outside this region, or beyond this region. And here, in this case, we gave up and just follow the Langevin equation. And then to calculate the transfer matrix like this, to calculate the, and if this time t is more than 1000, this matrix calculation breaks down. And then we switch to the focus on the largest, smallest positive Lyapunov exponent.
Right.
To study the entropy dynamics. Because in that region, the single smallest positive Lyapunov exponent determines the entropy. And others don't contribute to the entropy. But anyway, the entropy is decaying exponentially.
I see. But you said that you could calculate the QR decomposition.
Yeah, QR.
And then get the whole Lyapunov spectrum.
No, not the whole. Not the whole, only the smallest positive.
Okay.
Not the whole. I don't think I could get the whole Lyapunov exponent.
Okay.
If I remember correctly, we can calculate the whole Lyapunov exponent up to certain region like somewhere near here. And then I have to focus on the smallest positive one beyond that region.
Okay.
And it depends on whether you use Python or Fortran. With Fortran, you can calculate on Python easily breaks down.
Any more questions? Yes, no? Well, if there are no more questions, thank the speaker again. Well, as I mentioned, this is the last seminar of the Advanced Study Group. I want to take the opportunity to thank Team Simon for supporting me in this initiative and helping me. We thank also the participants who helped, everyone that is still around and who has visited, and PCS for the hospitality. It's been a great experience, lots of fun and lots of good ideas, especially Jung-Wan, who's been incredibly supportive. So thanks a lot for staying with us and for everything. Thank you.
I'd like to thank Bruno for doing all the real work.
I sure are without doing anything.
Small announcement, we have a dinner in the lounge, please grab some food and eat there.
Do we have something to eat?
Yes, over there in the BCS lounge, should be something.
Okay, thanks for your help.